Okay, so yeah, so now the idea is that, so we've been considering JT plus CFT, which is coupled to a bath CFT. But now, the thing that we want to do, or a crazy idea, but which somehow gave us a lot of mileage, is to consider this CFT to be holographic. Okay? So we have a two-dimensional holographic theory, which in this region of the space-time is coupled to JT gravity, and here it's just a holographic CFT in flat space. And the idea now is that this space-time is dual to a three-dimensional bulk coming out of the board. And the trick we're going to use is to compute the entropy of the bath using the standard Ryu-Takenagi formula in 3 dimensions in this new direction. So let me go over that, sort of how to think of that model and the calculation. So the first question is, what is the, yes, please.
I mean, let's assume it exists. So I would like to know, I mean, that the program is JT dynamical gravity plus CFT, I understand that. But you know, there is a dynamical gravity. So
let me define that. Well, okay. So the thing is, we understand holography. So if I give you a holographic CFT with background metric, actually this is exactly what I'm going to say. So if I give you, so let's say I give you some I CFT on some background metric G2. IJ. Okay, say I give you this. Then its 3D dual must satisfy the following relation. That the three-dimensional metric near the boundary, the two-dimensional boundary must go as something like 1 over epsilon squared. This is like the cutoff, like the distance from the asymptotic boundary, times Gij2, where these indices run along the boundary directions. Okay. So far, this is just standard ADS CFT for holographic theory on background metric G. So now something that I'm going to use is okay, Rajesh was not there for that talk, but let me see. So the idea, the quantum state, so I argued in my first lecture, the quantum state of, in this static spacetime is actually, it's the vacuum with respect to some coordinate W. Okay, so it's a Minkowski space CFT that is vacuum with respect to W. Okay, so the claim is that there's a plus minus 0 with respect to the flat metric ds squared equals minus d omega plus d omega minus. So the Hauking radiation can be thought of as Rindler radiation with respect to this vacuum. Given the CFT defined on this flat space metric and the state, we know what its three-dimensional dual is. Right? We know that the dual here in 3D is simply Poincare ADS 3. There's some new z coordinate which extends in the third dimension. Okay. So we let me see. Yeah, so let me draw another picture here where this is the boundary. So this is like a time slice here. And going down, this is the new holographic direction. Okay, so this is here we have ADS3. Okay, this is Z equals 0. Because, so here we're trying to find in the bulk we have ADS3. The solution is going to be locally ADS3. It's going to be completely determined by the location of the cutoff surface. The location of the cutoff surface is found by understanding how it's really by relating the cutoffs of the theory defined in this W plus W minus coordinate, or with respect to this ADS2 coordinate or the flat coordinate here. So there's a coordinate transformation between these guys. So some W of x. I should say here I have x plus minus with the metric ds squared minus 4 dx plus dx minus over x plus minus x minus squared. So that's what I have here. And here I have a coordinate I call y plus minus, and it's the flat metric minus dy plus dy minus. Okay, so now the thing that we need to do is the following. The way we solve for the location of the cutoff surface is in the following way. We equate the metrics. Let me just finish writing this, and then, so when you write this, you use this coordinate transformation, and this gives you ZW as a function of x plus and x minus.
So, when we discuss this amount with A, the boundary is going to have some part which is GT plus CFT coupled to HCFT. Entanglement between these two is going to look like this.
Yeah.
So there's some point which is, I guess, equal to 0 with respect to entanglement between one part and the other. Directions do not need
they are entangled at t equals 0.
LR are not entangled with BL and PR.
They are, right? It's
whether they're not entangled.
but it's small. They're entangled for all time.
It's small, but it's not 0, you say.
Yeah. Okay. And you can do something similar by for the bath. So far here, this determines ZW and for the ADS2 region. Okay. And similarly, you can also equate this to 1 over epsilon squared. I don't know if that was clear or not, but I'm using this boundary condition here.
So where did that small part come from on that side? I just didn't appreciate.
Where did that small part come from? I mean, there's entanglement. I mean, the pure state here, there's entanglement between this region and this complement. That's where it came from. Yeah. It's not quite vacuum, but yeah. dy plus, dy minus, and that gives you one sec.
In this holographic DT formula, you don't see that, right? You just compute that as a trivial slice. S bulk is and that this is the part that's coming from S bulk. Is this the part that's coming from S bulk?
That small piece? Yes. It comes from the trivial surface.
The trivial surface, which always has an S bulk. There's something on the side.
Yeah.
What happens when this ZW calculated for these two patches?
Let me draw it first.
Okay.
So the thing that so let me look at some time slice here. Let's say, and the cutoff surface looks something like this. It's not quite so I'm going to draw it like this. But it's not quite constant. Then at some point, it does something like this, and then continues like that. Okay. It's continuous. It's not smooth.
Continuous. Is it in formulas it's true. It's
Yes. So the thing that we have here, so I'm trying to this in 3 dimensions. What we have as you take epsilon to 0. So remember that in this x region we have a finite G Newton, right? So we have dynamical gravity in this region. That's manifested in this diagram by even after I take epsilon to 0. This thing approaches something like this, but there's still a region that's extended into the bulk. Okay. The way that happens is really it's because this thing is asymptotically ADS2. There's like an infinite amount of space here, and that's why you can push it all the way into near the boundary, but you still have a segment which really dangles into the bulk. So now the boundary here is like the usual boundary that we consider in ADS-CFT. That's where we often say where the boundary lives. But we also have a region here where gravity is dynamical. So this is like a Randall syndrome brane. Okay? It's part Randall syndrome, part regular ADS-CFT.
So we just mentioned we have to be more the boundary conditions that you impose at the point where gravity switches off, and will the effect what you.
Yes, it does. So we impose that it's, for example, that it's asymptotically ADS2 with some given value of the dilaton and so on and so forth.
I mean, isn't that important somehow in determining the precise bulk metric?
It isn't. It is important, but it goes into this procedure. It is important, but it's been taken into account, is what I'm saying. I should say that these coordinate transformations, these coordinate transformations, they are sensitive to the stress tensor, right? So for example, we know that we have vacuum. This is a vacuum solution in the bulk, just an eternal black hole. So the stress tensor in X is 0. But the stress tensor in Y is not 0, okay? Because there's radiation coming out. And this coordinate transformation has all that information in it.
So in a way, the coordinate transformation is the one which gives you the
Exactly. And so this function, Z of omega, really knows sort of some details about the state, okay? The evolution of the state as a function of time is captured by the motion of the cutoff surface in 3 dimensions. Okay.
It's not an asymptotic surface anymore.
Here it's an asymptotic surface, but here it's not.
I mean, so how seriously should one take this thing? Because if you have made a huge perturbation, for example.
Don't add a very huge perturbation. We're thinking. So here we're thinking of this. We're thinking of this. So this theory has to be defined with a cutoff. So I guess maybe that's the statement that you're getting at, right? There's a cutoff here. I mean, here, let me give you 3 different. Let me say a few more words, and maybe I'll mention that. So there are 3 different perspectives one can take in viewing this system. The first is what I'm going to call the no gravity perspective. Where the boundary theory, I mean, from the name, there's no gravity involved. So 1, no gravity. Let me just draw this, then I'll take your question. So we have the L, R, and VR. And you should think of the system as the following. We have a holographic conformal field theory coupled to a holographic quantum system. Similarly here, holographic quantum system plus holographic CFT. That's one perspective. Another perspective is the purely 2D perspective, so 2D, where the theory is the thing that we've been studying all along, which is, I'm going to draw it in the following way. I'm going to give it a curve here, just to emphasize that here it's flat space, and here we have ADS2. The idea here is that we have holographic CFD here. Here we have JT plus holographic CFD. And here again, we have holographic CFD. Okay, so this is what we've been doing so far. And then there's the third perspective, which is the purely gravitational description. So only gravity. Okay? So here in this case, again, you draw a picture like this, where you should think of this as a UV brane. Here we have ADS3. And here we have JT gravity on a Planck brane, using terminology of Randall syndrome. Okay? So here we have UV branes, the usual branes we think of when we do regular ADS-CFD. And here we have a dynamical brane, which has JT gravity living on it. And yeah, so in going from 2 to 3, essentially what we did was that we replaced the holographic CFD with its three-dimensional dual. But notice that the JT theory, it appears in both descriptions. Right? JT is not holographic in that sense. It's holographic to this. So I've been calling this holographic inception. You guys watch the movie Inception, the dream within the dream? So we have holography within holography. Right? That's the slogan here.
Can I ask you a question?
Of course.
So when you take ADS3, taking over all metrics in ADS3, action
Of course.
localizes
On this.
So, I mean, I'm a bit worried about this boundary condition. Metric. You know, what you're doing is you're creating a bubble of ADS2 dynamic in Gaussian space time. You're looking at the hologram of that. Now, this is a thing we discussed in the first lecture also.
Okay.
How legal are you in doing all this? Now, I mean, it bothers me again and again. But
You mean this aspect that so here we have ADS2, and then we did.
There's a junction here. Now, I mean, if you think in terms of ADS2, the cutoff is actually in some sense infinitely far from the boundary here.
Yes.
So this boundary condition is bothering me. Okay, that's fine.
Okay.
When you
I really
Is it bothering you at the junction? Where that point? Is that where it is bothering you, or where is it bothering you?
That is of course one part of the problem, the junction, but also the JT, the Planck plane. I mean, as a semi-classical thing, that makes sense. But I'm just wondering how since you're going to compute fine-grained things.
But I want to continue to work in the semi-classical approximation. That's the surprising thing here, that we can work in a semi-classical approximation and get sensible answers.
So rather than we know the answer we want to get. So,
No, but I'm not inputting that.
I know you're not including that, but because we know the answer you want to get, you know the approximation was right most factor because you got the answer you expected. I mean, it's.
Yeah, sure, but then you need to justify why this approximation is valid and so on and so forth, which you'll leave to graduate students.
please go on. I'm sorry.
Okay. No.
Because you're not staying beyond tomorrow. That's
Yeah, I'm going to be here tomorrow, so we can talk. But yeah. Okay. All right. So now let's compute the entropy of the left-right system.
Much more problematic in higher dimensions than that.
So you might think that, but with George Santos, I think we were able to, mostly he was able to find numerical solutions in higher dimensions. I think ADS5 and 5-dimensional bulk, which look like this. So you have, I guess, look like more like this. As in you have a black hole on some Planck brane, and coupled to some I guess, matter theory with some temperature. By that I just mean he constructed a solution in the bulk which has a horizon that looks like this. Looks something like this, I guess.
Plasma ball solutions. Is that what you get?
Say that again?
These plasma ball solutions.
Maybe that's
Very similar, I think.
no, it's slightly different. So let me describe what this spacetime looks like. It looks like you have a black hole in the bulk. The fact that you have a horizon everywhere here tells you that there's a temperature there. So this is like a Hawking state, and the horizon joins the Planck brane. That means that this horizon joins with the horizon on the black hole. The horizon of the black hole on the Planck brane, which is, this is really the picture that I have as well. It really looks something like this, but I've been ignoring this horizon. Seems like it, yeah.
It's a little different, but I'm just saying I just want to say it's plasma ball solutions, right? I don't know.
You mean the case where the temperature far away is different than the temperature of the black hole?
This is just a situation where you have a deconfined phase and there's a confined phase.
Okay.
So you have, and these two you can coexist for a while.
Sure.
So it's like a small black hole in ADS, but it's a more precise version of that because you take something which is, instead of global ADS, you take point cloud ADS.
Okay.
This black hole is limited by its transverse size.
I see.
It looks
So
like
there are these JNS solutions. But those are all, I think, with the UV.
everything is on the UV plane. So that makes me, so there you understand, I guess, this.
Yeah, but that is, so.
Okay.
Yeah. So by the way, I think that the metric here is is continuous along this entire thing. That's guaranteed by the fact that this thing blows up as you go over there. Anyways, so now we have this picture in 3 dimensions, and we want to compute the entropy using the 3D formula. Okay, so let me draw this thing again. Just the 3D perspective. Here's the asymptotic ADS boundary, and here's the location of the cutoff surface. And we want to, I'll draw it twice. Okay, so remember in 2D we had a trivial surface. Here I'm computing the entropy of LR or of BLBR. In fact, here that is given by. So we're trying to compute the entropy of here's BL, here's L, here's R, this is BR. Say we want to compute the entropy of union of LR. The statement is that the correct RT surface is the following one. Okay, it's supposed to be a semicircle. And this guy, the entropy of this is the entropy the area of this. Sorry, I should have emphasized. Now I am simply applying the HRT prescription in 3 dimensions. Okay, so I'm just looking for areas. The area of this surface is equal to the entanglement entropy of this surface, right? So this is just standard Ryuta-Kanagi.
And you should also, why don't you have the S-bulk contribution?
This is you mean here? There is an S-bulk contribution, but I'm assuming it's small. Yes. I'm assuming that it's not going to play a role, and so, yeah.
Because you're doing really semi-classical physics.
Exactly. Good. Good, yeah, I'm doing semi-classical physics, so I should have emphasized that I'm working in the following limit. So I have the two-dimensional G Newton is much less than 1 over C, the central charge of the holographic theory, which is much less than 1. Okay? This tells you I can work in semi-classical approximation in 2 dimensions. This tells you I can work in semi-classical approximation in 3 dimensions. And
There is the G Newton in 3 dimensions.
that's C. So this thing is G Newton in 3 dimensions divided by LADS.
So now you changed the logics because previously you had said that you can have few matter fields at the compound range.
Exactly.
Now we have to
There's an
choose large.
intermediate range. It's an
No, no, but
Yeah,
C has to be large.
But C has to be large compared to 1, but small compared to 1.
Previously, when we discussed,
But
C
that's
was
the
out of
range.
1.
No. It's just small compared to 1 over G Newton. That's
Previous
all.
discussions, the conformal field theory central charge was small.
No,
In-
not necessarily.
not
Just
necessarily.
C
It
is
doesn't
C.
have to
No.
be, but it
I think
No, it will
all-
just C much less than 1 over G Newton. That's all he used.
Yeah, in the earlier discussion, yes. So let me say. In the earlier discussion, I simply used this thing.
Yeah.
Okay, I was not precise about how big C actually was, just that it satisfied this. Okay, you can ask, was my previous analysis valid when C is order 1, like when it's very small? Something that I've been ignoring is the entanglement entropy that comes from the fluctuation of the Schwarzian particle. Okay, so I've been ignoring that. That gives you an order 1 contribution, and so in order to justify what I actually said before, you should take 1 over C to be very small, or C to be large compared to 1.
Number of degrees of freedom in the 2 dimensionals here.
The bath?
LR.
LR, yes, yeah,
That is much smaller than the number of degrees.
much larger.
Central charge of this LR in some sense, the effective central charge is larger than the effective central charge of the boundary.
Yes, of the bath.
Discussion, because you have an infinite volume factor.
That's how we can accommodate for all those degrees of freedom. Anyways, so yeah, so we have one RT surface, which is that. Notice that this is the same RT surface had I computed the entropy of LR or the entropy of BLBR, right? The minimality constraint in 3 dimensions imposes that these two must be the same. Okay? So here it's just a statement that the entire state here is pure. The entropy of this region is equal to the entropy of this region, right? So it's the same RT surface for BR or LR. There's another surface.
How does this affect the geometry?
How does what affect?
What if I took G Newton? What if I change some of these things? I understand how the bulk rule will change. G Newton became a order 1 by C.
Yeah.
How would the bulk rule change? The bulk rule picture. Order 1 over C when C is in 3.
So you want to consider sort of standard Rundle syndrome, essentially. And I think that the solution that George found, I described previously, a few moments ago, is in that limit, where the 2-dimensional G Newton is really of the same order, is given by G Newton 3 divided by LADS, but in higher dimensions. I think so, I'm not sure, but people have considered solutions that look like this in standard Rundle syndrome. And it might modify the calculation of the entropy somewhat, as in the corrections might be important. Exactly. So yeah, so the space-time, the solution might be there, but the entropy might be different. Okay, so now, let me remind you first, when applying the RT formula, your surfaces are allowed to, so often people consider these gapped states where you have this end of the world brane in the bulk. So you have some defect in the bulk. You're supposed to allow RT surfaces to end on that. In this case, we do have something like that, which is this Planck brane. So RT surfaces are allowed to end on the Planck brane. So you might have something like this. Usually in those cases, when you have this end of the world brain and so on, those defects are not dynamical in their internal, the action for that brain does not have an intrinsic Ricci scalar term, usually, so it's not dynamical. But here we have a Planck brain which has the JT action on it, and therefore you do expect to get a contribution from this endpoint, which is actually nothing but the area at the endpoint, which is the dilaton. Okay, so the RT prescription for computing the entropy of this RT surface is the area of this surface plus the delta function area contribution at this point on the Planck brane. So this thing would give you precisely the formula, which I don't have or erased. Let me just draw it here, I guess. Let me just draw it first. It gives you something like this. So there's the bulk entropy piece of this term, that's this, and then there's a dilaton here, that's this point. There was a question?
Can you say why is it allowed to end on the defect? What is the
so far, I'm going to give another argument soon. But so okay, I can say two things maybe. First is, in some sense, you're supposed to look for all surfaces that are homologous to the boundary. That means that that the boundary region and the surface are the only boundaries of some bulk region. If you have a brane in that region, it's a dynamical brane, so it's not really a boundary. So that should be allowed. So you're allowed to end on it. The second statement is in applying the Lukowitz-Maldacena argument for computing the entropy, it actually is sensitive to the Ricci scalar term on the brane. This is something I'm going to mention soon. When you do the Renyi calculation, there's a branch point on that brane, and you're supposed to branch points in the Renyi calculation give you area terms. That's a very brief and hand-wavy argument, but I'm going to go through it soon.
So we end it, like what is the prescription that I'm supposed to take of this surface at the same point partition, but not consider anything else in the tree. It's not like I'm completing the.
No, you don't take anything else in the brane. So you mean like in this region? Yeah, I don't take anything there.
Region in between. Between the two junctions.
Yeah, you don't, right? Well, you do take something from this region. This is like the entanglement wedge of this side. So, I mean, there is a bulk entropy term in 3 dimensions, which I'm ignoring.
What I'm confused about is that what is the computation? I mean, it has only one end in the boundary.
Computing the entropy you can think of it as computing the entropy of the left or right. Well, let's focus on this.
I understand the pair. So your claim is that the pair computes the interval left, right? But there's no. I should not put any interpretation to only the one half of it.
You're supposed to have in mind this picture. I'm computing the entropy of L. So I should look for surfaces that are homologous to this point. This is one such surface, because I can contract this all the way down to L. You can think of L as sort of living here, in some sense. I can contract this all the way down to this point. So it's homologous to this point. If L is confusing, let's think of computing the entropy of BL. So now we're looking at sort of this region. So you're supposed to look for RT surfaces that start here and end somewhere. Usually, so if there's no brane, the only place this thing can end was nowhere. It just goes all the way down to infinity. This is the usual thing that this half space CFT has infinite entropy. there's an IR divergence. But now you have this thing in the bulk, and so this RT surface can end there. In some sense, I mean, here, you can think of there being two candidate RT surfaces, this guy or this guy. This guy is infinite, and this guy is not, so this guy wins. Okay, this is that's how you should think about it.
I tried to compute the entropy of something slightly to the left of it, like a point slightly to the left of it.
That's it. Sorry, so to the left of L?
So it's just starting the RT surface in L and starting slightly to the left of L.
Yeah, but that's effectively what I just did, right?
No, not everything. It's like I want to compute the entropy of some region.
Something like this?
That's right.
Perfect. So what are the possible RT surfaces? There is this guy, goes all the way down.
Yes.
There's this guy. Or there's this guy. And it claims that this guy would win. Maybe, I think so. Yeah.
How do you know this?
You just need to do the calculation. Ultimately, this guy could also possibly win.
Somehow isn't this question of the junction we've been discussing. So somehow you take that point, then you move it all the way to the. So let's say you take those 2 points and you make them closer and closer, and then you move them towards it. At some point suddenly.
Yeah, no.
The guy starts winning, and before that the small guys are winning.
There is a discontinuous jump. When you go all the way to L, whether you include the boundary point or not. Taking the limit is different from saying you include the point. And this is something I'm going to get back to later, actually.
Okay, then that would worry me about having a smooth bulk metric, because you have this discontinuity on the boundary and the entanglement. Why is it the metric is smooth in the bulk?
RT surfaces can jump. Actually, it's continuous.
No, but this is the RT surface is
Every itself is continuous. It jumps exactly in this way.
I mean, yeah, sure. The RT surface, the entanglement, the extremal guys might jump. That can happen, but this is different, right? You have some. It's, I don't know. I would worry about having a smooth bulk metric precisely to do this. It's a different jump from taking the resource.
So a smooth bulk metric, because the bulk metric is smooth. It's fine.
It's the same issue of boundary conditions that I guess we've been discussing. As you take these 2 points small and you move them to the right, there's a jump. Something discontinuous happens.
In the computation of the entropy, but not in the space-time. Space-time is all smooth and it's fine.
Why does something discontinuous happen then?
It's just a prescription for computing entropy. It's sensitive to what you mean by including this point. If you either take the limit or you actually include it. And I'll give you, in my proof of this formula, of this prescription, this thing will be apparent.
Should one think of some co-dimension, in addition to this brains, lower co-dimension effect at that point?
Sorry, are you talking about this picture here?
In the bulk.
In the bulk, what about it?
So you have this brain, this UV brain, which has
this thing?
Yeah. But then should one add a zero brain if this, at that junction?
No. You're supposed to think of this bulk geometry as dual to this quantum system.
Yeah. No, that's fine.
But this does not mean that there's a zero.
Kind of effect.
Yeah, it seems like if you do that, you're adding new degrees of freedom. So it doesn't seem necessary to me, but.
And the fact that this central charge of PCFT went into what geometric feature into the feature?
It's the LAD, it's the G Newton of the 3 dimensions.
That's the 3 dimensions, but the 2D open rod had some number of degrees. The shape of the frame.
Good. This is important. First, let me just draw this as I drew it before. You can ask, what is the bulk theory that I have? The bulk theory is, I have 1 over G Newton 2 dimensions. ijt of G2 plus 1 over LADS, is that how I should write it? No, what am I doing? 1 over G Newton 3. So this is a 2D action. You have a 3D action of Einstein-Hilbert, whatever, R plus lambda. Okay, sorry. G3. So I have 3-dimensional Einstein-Hilbert. This is the action everywhere in the bulk. But I'm explicitly putting a boundary term on the Planck brane. No, the entire Planck brane. You mean which is part of the UV brane? That's what you meant? Yeah. So I'm putting this 2-dimensional JT action just over here, but I'm putting this in by hand. Right? This G Newton is not related to this G Newton 3. It satisfies what I was saying here, and so the shape of this Planck brane and so on can be thought of from the 3-dimensional perspective as you need to find the location that satisfies whatever equation of motion that you get from this combined action.
And there are also Gibbons-Hawkins terms.
Yeah, there's those Gibbons-Hawking, yeah.
Something like a really, yeah.
You can study this effective action and it will make sense and you can find solutions and everything.
Usually we can't do that. Usually you can't take gravity and add like terms by hand in some parts.
No, yes, you can. From a bottom-up perspective, you can just put in wherever you want.
I mean, if you, that's
Yeah,
why
boundary condition, right? Plus the boundary condition.
Oh yeah, of course. Plus the necessary boundary conditions and so on.
you're allowed to put boundary conditions on the asymptotic. That's what the Planck brane is not somehow asymptotic. That's the, I mean, otherwise
No,
you
I'm
can
not.
gravity in this room and just
No. I'm not putting boundary conditions on the Planck brane. Right? No, I'm integrating over G2, all possible G2.
and G2 is
Yes. It's a limit of G3. But the limit of G3 is not frozen on the Planck brane. It is frozen in this region.
of the Planck brane are also subscripts.
Yes. But luckily for us, JT gravity is really silly or stupid or whatever you want to call it. It's very simple, so it localizes to ADS2. That really facilitates the analysis of this model and why would be more confident than other cases. Okay, so let me go back to the entanglement entropy computation. The idea is this. So this RT surface is the disconnected surface. This is the trivial. So we've reproduced the two different RT surfaces in our 2-dimensional analysis via this HRT prescription in 3 dimensions. And I emphasize that SBL-BR is automatically equal to SLR in the computation of entropy holographically in 3 dimensions. This is imposed by the minimality constraint. So let me see. Let me say now a few words.
This is true in both the cases.
In both the cases, yes, at all times. So these two. Now we can let's study the behavior of these two candidate RT surfaces. So this guy here, the claim is that it reproduces this answer, that the entropy simply grows linearly in time. The way you should understand that is that as a function of time, if you sort of fix the cutoff epsilon, as a function of time, what happens to this cutoff surface is that it moves closer and closer to the boundary. Okay? So if there's no cutoff surface, the area of this surface is actually infinite. It's finite because we put a cutoff. But as a function of time, we are revealing more and more and more of this surface, and that's why the entropy grows. Okay?
First it falls. It was close in the past, and then it falls, and then it goes up.
Exactly. It comes down, then goes up.
Dynamics and things that happen with about 3
That action, that's all I can say. But
So I mean, what should be able to show somehow that you take this blank brain and it's far in the past and somehow it comes down. I mean, that's somehow the key point.
yeah.
What makes the brain fall and then go up?
Yeah, what would do that? That's a. Say that again. Yes.
What is it?
I don't know. I didn't study that. But I think for all time the horizon intersects the Planck plane. No, does it?
Horizon in this discussion. Higher temperature.
So that's presumably below, right? Otherwise,
No, but at. Yeah, the horizon is somewhere here. The question is whether it intersects the Planck plane at all time or not. I suspect actually at t equals 0 it might not intersect it.
Okay, maybe so that's the absolutely disentangled case. It doesn't
Yeah.
intersect and then everywhere else it is.
Yeah, maybe something like that. That would be actually interesting to study.
It goes inside the horizon and
Yes.
This comes out because
Yeah.
it goes inside the horizon and ends on the brain inside the horizon. It never comes out of the horizon.
No, this thing. This RT surface. If there's a horizon like that, then it must hit the horizon and come back out. I think this happens. Yeah, usually they don't. But because we're computing the entropy of the union of two regions outside, the only way to connect them is by going through the horizon.
This is like if you take the middle backward and take
Exactly. Okay, so we understand how we get this growing entropy. It's because we are revealing more and more of the RT surface. Yeah. Okay. Entropy of this surface is the area of this surface is infinite without a cutoff. The evolution of the cutoff as a function of time, as they evolve both sides up, is that the cutoff surface moves closer and closer to the asymptotic boundary. That was your question. Why does the cutoff surface go from the asymptotic boundary, come in, and then go back out? Because it's going out, you are revealing more and more of the RT surface. And this gives you a growth of the area and therefore the entropy. And that's why the trivial surface gives you this guy, which keeps growing. This guy, the extremization is of the two things, is they're independent of each other.
Just to understand, in this Hartman while the same calculation, I thought first it grows and at some point the RT surface is bit this start fading.
Yes.
But that doesn't happen here because you have only 1 point.
Exactly.
It has to do this discontinuity. Like if you do two intervals, then maybe at some point there'll be these surfaces.
Yeah, and then it'll break. That's what's going to happen.
What is the horizon of the? There is no horizon. There is a horizon in the 3 dimension.
There is a horizon in 3-dimensional theory, but it doesn't play an important role in this story. Yeah. Okay, the second statement I was going to make is that in the disconnected case, it's a separate extremization of these two. Right? So it's this guy by itself and this guy by itself. You're supposed to extremize the area of this surface plus the dilaton. And because of the boost symmetry, this will give you a constant answer. Okay? And that's why you'll get this guy. And you find that the location of that point is near the horizon, blah, 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 blah. Okay? So that's how you get this constant surface. And the minimality.
Where did the dilaton in this bulk
From the fact that this brane is dynamical. When you consider an RT surface that ends on a dynamical brane, you pick up an area term from that brane. You can prove this.
bulk contribution also in 3.
There is a bulk contribution, but I'm ignoring it. Because it's an order 1 thing. That's how I'm thinking about it. I don't have a CFD here with some central charge, some large central charge or whatever. I just have a bulk theory with an order 1 number of fields. And it's much smaller than 1 over G Newton 3.
One more thing, as you said, the horizon
horizon is dynamical because it crosses the time plane or maybe the time.
I don't know if the horizon is what moves or the cutoff surface, or maybe that's not an invariant thing. Like what's the?
There's a cutoff surface and then there's a but I'm just worried about the Planck plane. I mean, I guess there's some part of the cutoff surface which is the left to the right.
Sorry. Now I think sorry.
Fix one thing as the coordinate, and then you have to see one of them. Maybe the question is, I mean, can one write down a really precise metric and compute? That's it.
Sorry, I wasn't listening. I was thinking about something. One second. Give me a sec. Yeah. Okay. Go on.
The question is, can one write down a completely precise metric?
Yes.
One can.
We know everything about the solution. Yeah. I mean, I can't write it down right now, but we know what the metric is in the bulk. Like it's exactly that.
Say it's the Poincare, it's just.
And then we know what the cutoff looks like. You can, so something which I did not do is extend the horizon, the two-dimensional horizon into the 3D. That's something that I did not do. Yeah, it's actually not even, I don't think it's,
You don't need to have a geometry with a horizon.
I agree, you don't. Yeah, it's gonna look something like this. I don't know. It grows outward somehow like that. But I'm confused about the thing that I drew before, and so I don't want to make any definite statements now about what the horizon looks like. But a statement that I do want to make is that so we now have the page. So we have this automatically, and we have the page curve for both the left-right system and for the black hole, for the radiation. So let me make a few points. The first point is that it's interesting how the Engelhardt wall prescription in 2 dimensions of extremizing area plus bulk entropy is equivalent to an HRT prescription in 3 dimensions. I think that gives more sort of justification for that formula. Okay, I wanted to make that comment. And something that happens here after the page time. So after the page time, we have this configuration. There's something called the entanglement wedge of the radiation. So the entanglement wedge is everything enclosed by the boundary and the entangling surface. So that's this entire region. In particular, this region here. This region here is the inside of the black hole. It's this region. Okay, maybe this is not the best picture. Whatever, it's this region. That's the island, exactly. So this prescription automatically gives us the island. And here, it's more manifest, this idea of entanglement wedge reconstruction and how after you build up entanglement, you get access to the interior. Okay? Again, this is a manifestation of ER equals EPR. Yeah, so
Let's say you try to ask, you took some operator in acted into the state.
So it's an operator in L. So that, but at what time am I?
So it's the time when actually some intermediate time between page time and 0 time.
So okay, so prior to the page time, so there's an operator in L which acts, let's say in this region here.
That's right.
Okay, that's like somewhere here. Okay.
Right. find the entanglement where the LR is fully.
Much of LR is a full interior. Yes, yes.
So let's say you did O, you took some operator O, you acted to the state.
Yes. On LR.
On the full system.
Okay, okay. Sure, okay.
Then in this mirror operating instruction, you look for operator O tilde, which acts the same way. So you write O on side equal O tilde side.
But sorry, but the operator whose mirror we're trying to find is where? So we're trying to find the mirror operator of this guy.
Also somewhere there, that's right.
Okay.
And so now the question is, O tilde is, can you find O tilde that lives only in R? R is a full interior.
So let me see. So you want to find the operator here.
No, I want to find the operator in the interior.
The operators in the interior depend. They're left-right operators. They're not just right.
They can be left or right.
No, they have to be left-right. No, not can be. They have to be left-right
Yeah,
operators.
sure.
Okay.
Can I find? I mean, there's not public extracts on the right over.
In that sense, sure. Okay.
Can you find an operator only in LR? Outside is equal to O inside. This probably also in this QVC construction.
Yeah, sure. You might get something like that.
So the question is that the
Okay.
solutions for O tilde can be found in R in the intermediate time and then they stop being found in R. It's quite clear that you can't find them only in R after the page time.
Yeah.
What is confusing me is, and it's quite clear that they have to be in R at the 0 time.
Okay.
Confusing me is in the intermediate time, they're still in R and they
Yeah.
have to go into ELPR.
And then they transition to the other thing.
Maybe they're not completely now, but they're kind of approximately now. But at some point of time, really becomes uneven. Each time is really.
No, but that's a word that there's a sharp transition there. I mean, this may be something obvious. It may just happen immediately. Just by thinking about that.
Maybe just that it becomes order one or something.
There's a sharp transition. What is a sharp?
That's really because of large N here.
Yeah, so large N is fine. So the large N is, I think here is just manifested as being input.
Yes.
Maybe it goes from 1 by n to order 1 or something.
Yeah, so does that happen?
It never jumps, but it really becomes order 1 at some time.
So it's not going to be anything.
I'm just saying what happens in this.
I'm feeling it's probably happen immediately.
I'm not sure what happens in this construction. Similar thing should happen.
Okay. So it seems like we have evidence for a formula like this. B is like the bath, for example, so if B is entangled with a gravitational system, you're supposed to allow for possible islands. You're supposed to extremize over these I's. Things that those that extremize is functional.
Sorry, the answer to the question asked earlier that you can find O tilde only in R. Is it claim that you should be able to find O tilde only in R?
Prior to the page time, it's not going to be only in R, it's going to be in LR.
Yes, it's
Okay,
LR and
so-
R is a question of whether you look at right.
No, but even if you only look at left or right movers, there's also the identity operator on the other side. I'm saying that's important. That's
Yeah, fine. LR, yeah.
Okay.
LR, the question is between LR and ELPR.
sure. Yeah, then using
The statement is that it should be in LR. For the page time,
Yes.
it suddenly transitions to being in PL time.
yes.
But is it? And this should
This happens in I guess I think there are examples of quantum error correction where this happens. I don't see a contradiction for why that
I
can't.
don't see a contradiction, but it's just, it's a little confusing that this happens immediately, right? You don't see any simple reason why this happens. I agree there's no.
I'm pretty certain it's connected with the fact that we're working in large N. The reason why it's so sharp.
So the construction that you guys did, in this setup where we have a PL and PR, I think the expectation should be that
Yeah.
after page type,
Yeah.
you need the BLBR operators.
Yeah, it's essentially what you were saying, Subrat, the other day, right? The BLBR after the page time is maximally entangled with the LRs with the BLBR. And that's why you can, now the mirror operator will be in the bigger
You
system.
should be able to see this immediately.
Yeah. Okay, so we have a formula like this. If you want to compute the von Neumann entropy of B, you're supposed to compute the von Neumann entropy of B union I plus the area term. This equation seems very weird because there's a von Neumann entropy on both sides. You're supposed to interpret this in the following way. So this is in some sense an exact answer, but what we seem to be finding is that there's a prescription where we can compute it in the semi-classical approximation. That's what I mean by von Neumann entropy here. That you compute this in the semi-classical approximation, assuming that you have the semi-classical state of the quantum fields everywhere here. In particular, these are, let me tell you some confusing aspects of this, which is, it seems weird, right? So the thing that we want to say is that the Hauking radiation by itself actually contains the information. Right? There's Hauking radiation here. By contains the information, I mean its von Neumann entropy is small. But in the semi-classical approximation, this Hauking radiation is entangled with the Hauking radiation behind the horizon. So in the semi-classical approximation, the state of B is not actually tending to a pure state. The entropy is large, okay? And it keeps growing with time. But the statement is that when working within the semi-classical approximation, we have a prescription that will give us the correct answer. This didn't have to be true. This is some magic that we seem to have found. We're trying to understand why this is true. But in principle, we're still holding on to the idea that really the actual density matrix of the Hauking radiation of this region is actually not thermal, okay? But we want to see that. So far, I've shown that indirectly by computing by finding this new prescription for the entropy of B. Okay. Any questions? All right. Okay. Now is the last part of my lecture series, which is to redo Hawking's calculation more honestly. In fact, when we stumbled upon this, we were very confused as to why people didn't figure this out a long, long time ago. So let me explain. So again, we consider the same setup. This space-time, or this state, can be thought of as coming from the following Euclidean path integral. Where here we have CFT on flat space, any CFT, doesn't have to be holographic, could be a free scalar field if you want, massless. And in this region, we have JT gravity plus CFT. I'm defining a path integral to have this structure, where in some region I have just a flat space CFT path integral, but in some other region, I have some boundary conditions here where the metric is ADS2 for this JT theory. And I'm integrating over all metrics and CFT degrees of freedom in this smaller half disk. One can consider the full Euclidean path integral, so the bra and the ket, and I guess it looks something like this. I'm going to draw it as a square now. I should emphasize this is not really I mean, I drew it as a semicircle. That's just because I brought, as in there's no boundary here. I brought the infinities down to a finite point. But usually you send this to infinity, and this is just a half space. Okay, which is, I guess, what I'm doing here. And we have a circle in the center like that. Here we have JT plus CFT, and here we have CFT. Okay. Now say we want to compute the entropy of a subsystem here. We call that B. The union of these two guys is B. So that's somewhere here. The way that we compute, so the thing we're trying to compute is trace rho B to the n. You achieve this by adding a branch point and a branch cut, like this. I guess I should have said, I'm going to compute the entropy using the replica trick. The way you do that is you consider the replicated manifold, which looks like this. Where these different sheets are identified across these cuts. And on each sheet, we have a JT theory patch. Now, evaluating, so the way you compute entropy is you evaluate trace rho to the n, trace rho to the n for a different n, and then you analytically define the analytic continuation in n. You work near n equals 1, take the derivative with respect to n, and that gives you the entropy. So in evaluating this path integral for different values of n, we're supposed to allow gravity to do whatever it wants in these regions. We're supposed to consider all possible saddles, for example. One possible saddle is where each JT theory, on each sheet, we just have the hyperbolic disk, on each sheet. So when working on the branched cover, we just have all my branch points, and here I just have ADS2, it's a hyperbolic disk. Okay, that's one possible configuration, and I claim that this gives the usual semi-classical answer. So I'm going to say this is the, I'm going to call this the semi-classical saddle. Which gives the semi-classical answer. Okay, whatever. Gives the Hauking answer. Okay? But then there are other configurations and other saddles. In particular, there's one where the different sheets are connected by wormholes, and so on and so forth. The claim is that these wormholes can be represented on the branched cover. I know it's really cool, but relax. So you can represent this wormhole connecting these different regions. I should say that this is I'm only considering configurations that respect the replica symmetry. That's an assumption.
When you specified the state, there was a t equal to 0 point for the entanglement.
Right here, t equals 0. That's special too.
Go on into a later time, then you will have the whole thing with of states where the disentanglement happened on a t equals 0, but there's some other value of t.
Yes.
And you say.
Yeah, so the idea ultimately you should think of this as computing it t equals 0, but then continuing to Lorentzian time to whichever one you want. But now, okay, the punchline here is that these wormholes can be represented on the branched cover by an additional pair of branch points and a branch cut. Okay? let me sort of draw some pictures for example, the n equals, let's consider the n equals 3 case. You can have as many as you want. But for now, let me consider the emergence of just a single one. But this corresponds to what I drew here. Let me be a bit more precise. Let's consider the n equals 3 case. Okay? So I have 3 copies. And the wormhole is something like this. Okay? And what I mean by that branch cut is there's another point in the background. Is that clear? So this point here is like this point, and the other point on sort of on the far side is this point. And this this line, which was dotted, is like that cut. It's the fact that if I go through this line, I go from one sheet to the other sheet. That's doing something like that. Okay, and when working,
if they had like the 3 intervals, one finite interval, and if it was drawing an elliptical geometry to compute any entropy of that.
So, but sorry, what do you want me to add? So this is 2 half spaces.
Yes. So if I just added, like a finite interval
Here? No, you're not allowed to do that. But you want to do that. Okay.
I do that, and I try to draw the geometry, the elliptical geometry.
Yeah. That? Yes. I don't think that's a sensible thing to do. You can't just add an interval in the gravity region, because gravity is going to fluctuate and so on and so forth.
Yes, so let's forget about that. Ask is a different question.
Okay. So you.
I'm just trying to understand the geometry.
So we just have this, no gravity. So just this?
So this will give an elliptical geometry.
Yes.
So when you add gravity, is the elliptical geometry similar?
It has the same topology, but what gravity does is that it smoothens out the branch points. So given this, where I literally have flat space here, these branch points are not smooth. Right? For example, if you consider the expectation value of the stress tensor, they diverge at this point. But what gravity does is that it smoothens it out by giving you these nice wormhole solutions. The point that we were talking about is this guy right here.
So normally you would integrate over those points.
You would integrate over those points. And that's in integrating over the gravitational configurations. And the saddle point, the equations of motion, fix the points at a specific location. And before I tell you what that location is, that's the extremization, exactly. So the point here, so working near n equals 1, the metric here, working near n equals 1, the metric here is just ADS2. Right? At n exactly equals 1, I just have the usual disk. So working perturbatively about n equals 1, the answer that you get is that, so as Loga, I guess, was trying to, maybe hinting at this, if I draw this picture for you and I tell you you don't have gravity, we are computing this quantity, right? This is B, and this is that region I. From the branch points, we get the dilaton contribution of phi at the boundary of I. Yes. What gravity is doing for you is that it's dynamically generating branch points and a branch cut. That's what it's doing. And we understand why this formula, as in why, now we understand this prescription of saying you work in a semi-classical approximation. because when you take n goes to 1, that path integral is the path integral which prepares that harder Hauking state, if you will. And the equations of motion, the equations of motion give you this. I should say that we haven't, this paper we're still working on this. There's some subtleties, but it's really in the examples that we worked out completely, we see this. The equations of motion imply the extremality condition. And then the minimality constraint is imposed by the fact that, that different saddles are weighted differently. They're weighted by the generalized entropy. Basically, roughly speaking, you get something like this. Trace rho n b. Well, first of all, this is something like e to the minus n minus 1 phi over 4g Newton. So first, now I'm going to work near a gravitational saddle. So this comes from the gravitational equation of motion, plus trace rho CFT n on this saddle. Okay, so this is why, and this density matrix is a density matrix of these three regions. Okay, and this thing ultimately is going to be e to the minus n minus 1 phi over 4g Newton plus the von Neumann entropy of B union I. Okay, so you see?
Understand how you get -1 the second term.
That just comes from just standard.
You would get the n, because that's the n goes to one limit. Yeah. Okay.
Yeah. As in, if you ignore this and I just give you this, and you take derivative with respect to n near n goes to 1, you just get that thing. This is just the usual computation. But the idea is that this thing has a sum over saddles. And this thing is weighted by G Newton, and so one of these guys will win. Okay. So we see how we can get this nice formula from a very simple calculation, a very standard calculation, just honestly compute trace rho to the n, include all the saddles. And
the calculation or in the 2 dimensions.
I mean, all of this is the 2-dimensional picture.
In the sense of, what I'm saying is that suppose I take 2D gravity, JT gravity, for classical solutions which have vortex-like singularities, so that the radius of curvature is infinite. What are these solutions?
No, but we're not doing that, right? We're doing it at
You're looking at branch cuts in JT gravity.
we're doing it at finite n first,
Yes.
and then we're continuing.
Get the right answer if I just do what I was.
Actually, there is a trick. You can directly work near n equals 1. So then it would be then yes, you would be solving JT gravity with some conical deficit. But there's a prescription, okay, of Locos and Maldacena, where you're not supposed to take the contribution from that singularity at the conical deficit. And this is justified by saying that you first work in the integer n, where there's no singularity, take that answer and then continue it down to near n equals 1. So that's why that doesn't contribute. Yeah, exactly. This would be just area in higher dimension.
So you're saying in principle one can do this in higher dimensions?
Yeah, so the thing is, the effect is so simple, we expect this, the JT gravity has these wormholes, higher dimensional gravity also has these wormholes. And so we expect that the same thing would happen, will also give us the same answer in higher dimensions. Let me say one point. In JT, to completely justify this calculation, one first needs to do it for integer n, show that you have saddles, and then continue n goes to 1. That's the continue in n and go and take n near 1 and blah, blah, blah. Even in JT gravity, we actually can only solve it for like n equals 2 and maybe 3 max or whatever. Otherwise, we can do it numerically. We can show that there are saddles numerically. But that, again, just to justify the calculation, you can work directly near n equals 1 where you can solve everything, and you get the right answer. And so I think in higher dimensions, that's the most you can do. Higher dimensions, you can say, let me work near n equals 1. You know what the geometry looks like there, and then run this machinery, and it'll give you the same answer.
The saddle point shifts to having these wormholes at the edge.
Exactly. So you have two contributions. You have the semi-classical saddle with trivial topology here, and that will give you the Hauking answer. So that will give you the Hauking answer and all the history of studying evaporating black holes in CGHS and so on and so forth. That's a semi-classical answer. But now if you include these different Renyi solutions, for example, these wormholes, that would give you a different answer. And I think this would correct all this work of, for example, Sandeep and Strominger and so on of evaporating black holes in CGHS and so on. So essentially, they missed this contribution. This is?
The page time here was beta log.
No, the page time here is beta n. Beta times SBH. And the idea, again, so yeah, I'm doing everything at t equals 0, but you can continue this to Lorentzian time and so on. Yeah, I wanted to give some examples of applying this formula. Yeah, there could be. You need to find them. For example, you can have other topologies. Put a hole there, and so on and so forth. But I think these guys are. I suspect they're suppressed because whenever you increase the genus, you need to add. So I've been completely ignoring this. You need to add other factors of S0, the ground state entropy. And so these terms are disfavored. Contributions are disfavored.
Why did I even need the non-gravitational CFT? Why can I do this just like de-Sitter black holes? Because the argument seems so general. Where did I need this simplification? I thought I think of something.
How are you?
Then creates that, and then I think of these terms outside.
Well, where is this outside? So here I had a crutch that I can define these intervals are fixed, even as I sum over different gravitational solutions here. But in a theory where it's gravity everywhere, it's going to be a bit more subtle. But perhaps there's a way of analyzing this. In fact, we're studying this in the case of CGHS, where still work in progress. But yeah. But you can directly let me just keep it at that. Let me emphasize one thing. So if you've been paying attention to talks of Stanford and Schenker and Saad, they also consider topologies which look like this when computing this Z star or whatever. And there they had to include contributions from wormholes where they had to integrate over the modulus, which is the size of the circumference of the wormhole, the size of the width of the throat, because it was not a saddle, right? They could not find a saddle. But here we have a saddle. The CFT stress tensor supports the size of the throat, and you find a saddle point.
When the ramp starts.
Yeah, let me see, where was that? I think it's where the ramp starts. Yes, yeah, the ramp comes from that topology like this. Yeah, that's right. From the,
During the
yes. I wanted to give examples of how this line of thought gives you answers you naively might have not expected. So let me give those examples first. Say, okay, say we compute the following thing. This might be too small. Say we want to compute the entropy of an interval that hits the ADS boundary. Okay, so it really touches it there. So the picture that we have, the Renyi calculation, you have this thing there. So the asymptotic ADS boundary is it's not a product of circles. It's one big circle, right? So it goes. So if you go in here, you touch this point, you come out there, and so on and so forth. So this tells you that the Schwarzian, for example, or at least one configuration for the Schwarzian, should also, or said differently, the ADS solution that you patch in here must also have a branch cut and a branch point somewhere, and so on, because the asymptotic boundary it connects at different sheets. When you fill this in via this ADS saddle, it would also connect. This branch cut would extend inside, and you can go to the other sheets by winding down. The reason why I drew this, I consider this case, is that this derives the entropy formula for computing, let's say, the entropy of the right-hand side. Right? You can take this point to be very near the boundary, and this answer. So can we have that? So this would say that the entropy of, let's say, the right-hand side is given by phi at this point u, or 4g Newton, plus as bulk sigma u. So this entropy region, this entropy there. Okay. So just pointing out that these same set of ideas derive for you the Engelhardt-Wall formula, even for computing the entropy of the right boundary. So I've taken one point to be on the boundary, and I'm taking the other point sort of as a limit towards the boundary. That's how I'm defining the right boundary. And this is essentially, I mean, people have discussed this, something similar to this. I'm just emphasizing that this set of steps that I've outlined is what, for example, Lowkowitz and Dong used to prove the generalized entropy prescription.
What does this look like as a function of time?
It's constant.
It's just constant.
Yeah.
It sits.
Yeah. Yeah, but I'm just pointing out here how this filled-in gravitational solution generates for you the branch point and the branch cut, which comes about because the asymptotic boundary winds across the different Renyi sheets. That's all I'm emphasizing. And let me now talk about a much simpler case, but also surprising case. Let's consider the following thing, where we compute the entropy of the entire bath. Okay, so entire bath including these points. Something like that. Okay?
The points in the end.
I'm including these points. Everything.
That should just be 0.
Good. This should just be 0. How do we see that? So notice that this part of the ADS boundary is actually joined to just this part of the ADS boundary. Right? So if you consider these two paths, that hits this point and this point, they just come out here. So secretly, what this picture is simply the following. The bottom half here simply connected to the top half there. And then you fill in each JT region with an asymptotically, with hyperbolic space. This thing is nothing but the expectation value of the Hartle-Hauking state. I'm just defining the Hartle-Hauking state as this path integral. To the power of n, which is simply 1. So it does not depend on n. Completely factorizes, you compute the entropy, you get 0. So the state of this region is actually pure. So when I draw the space-time, these Renyi entropy considerations tell you that the entire these two regions, well, it tells you that the semi-classical picture that you have some local quantum field theory defined everywhere is inaccurate. This region here is actually part of these two. And and I think this is, I really think, to conclude, I think this is an interesting observation, and I think it's I think we're making progress on the information paradox, and it really seems that this is a general statement. So I think that's all I had. So let me stop there. Thank you. Questions?
Sorry, please go ahead.
I have a slightly harder test case I'm wondering. So let's say we took N and then we took a region and we allowed that region to expand at the speed of light. I mean, I somehow wanted to see that the LR. So let's say we started equal to 0, and so LR has an entanglement, which is the minimum entanglement, I guess.
Yes.
And then we allow the we allow the maximally entangled with each other. That's when they're in thermofield state.
Maybe you can say it that way, okay?
And then we allow we take a region that grows at the speed of light somehow.
What do you mean by region? Is it, so like this?
Time dependent.
Like these regions?
Region, I want to compute, well, at every time slice I take a region.
Oh, but are we taking this region or its complement, like this thing?
I want to really take a region between 0 to x on both sides.
Yeah. So it's this thing. So.
That's it. Now this guy should always stay fixed. I mean, somehow because the entanglement doesn't get faster than the speed of light. Is that a reasonable assumption?
Maybe the entropy of this is fixed. Let me see. So I have Hauking modes. So there's Hauking modes that do this. So this thing does not increase the entropy because this thing is running away. What about the complement? I have this.
Yeah, there's some stuff coming in.
So this guy is entangled with this guy. No, this guy is entangled with something here. So it doesn't actually.
Maybe stuff coming.
I don't know. I'm.
Entanglement went to an object of this region. And there was information about the full interior and LR at time 0. Now if you make LR go at the speed of light, presumably that information doesn't go anywhere. It stays.
Maybe.
At least the entanglement wedge of this should be equal to.
Yeah.
Is it easy to see that?
No. You can apply the extremization procedure directly to that space-time. So you don't need to go through this proof and so on. It's not immediately clear to me right now, but if I draw these these Hauking modes more carefully, maybe I think one can show it at that level, is I guess what I'm saying. It's not a difficult thing to show.
We don't have speed of light, just have the speed of entanglement. The speed of entanglement, which I'm guessing must be larger than the speed of light. Is the speed of light
Yeah.
speed? It could be smaller. It could be smaller.
Could be smaller. Actually, I just remember that I have examples, interesting examples, where the island gives you non-intuitive, counterintuitive results. If there are no more questions, let me first take questions, and then I'll get to that later.
Calculation. That is some overall
Saddles?
quantical geometry. So
Yes.
is regulator to give me the right answer.
Yes. Yes. Yes.
It has been done in this calculation.
It's been argued for. I don't know about done. But yeah. But
On the basis of what you say.
yeah, but also yeah, for and also an arbitrary dimension and so on.
I mean, you just take the JT gravity on the Poincare disk.
Yes.
Classical solutions we look at. You can think in terms of more singular classical solutions.
Yeah, yeah. Then the metric is non-trivial there.
Yeah. Partition function, some overall.
Yeah, yeah.
That will give you the partition function.
Or
Trace row to the n.
do
Yeah.
this type of calculation.
Yeah.
I'm just saying that I was asking whether that gives the answer.
Yes.
The answer to what?
The answer to what he's calculating is.
Yes, it will, and the claim is that at large n, one of these saddles will dominate. I should also emphasize that this formula, remember we said that it implies some sort of holography, that the inside is dual to the bath. But I didn't need to assume n equals 4 super Yang-Mills or anything like that. Somehow the Euclidean path integral, gravitational Euclidean path integral, already knows about this. I think that's a deep point. And yeah.
It's a statement that the gravitational path is also possible.
Yes.
It also gives the area.
That's right. That's right. Yeah. Yeah. That's right. I'm trying to square this with this notion that you should think of JT gravity as a disorder averaged theory of these, for example, different SYKs and so on over the coupling. Yeah. This discussion seems to say, for example, that you don't need the firewall, right? So the fact that the entropy does something like this, the fact that the interior is now part of the exterior, you don't run into the firewall paradox. But as emphasized to me by Douglas Stanford, he says maybe this is like in the same way that their two-point function or their z star, if they compute it using JT gravity by summing over all the saddles, they get an answer which is on average correct. Right? So the entropy, the two-point function goes down, then it grows, and it stays at there's a plateau. But the answer from a single realization of SYK has all these fluctuations. And I think that maybe what's happening here is that we're just computing the average somehow. Like we should expect the entropy to look like this on average. But there might be fluctuations and so on and so forth. And so then that's why one should not make a completely definite statement about there not being firewalls. There isn't a firewall argument, the standard firewall argument, but who knows about what can happen behind the black hole horizon. Maybe there's another argument to say that the space-time should not really trust it too much. So I wanted to make that comment. Yeah. Yeah, but let me see.
So that would answer this
Yeah. It might actually even be that within a single realization, one can't really formulate the information paradox. That's possible. Like you don't really have a nice black hole and this Hauking radiation and so on. That might really be an average statement. I really think that this is a resolution of the information paradox as stated by Hauking. Right? He considered a classical geometry, a semi-classical geometry, and you have these Hauking modes, and this is how that's resolved. But we haven't yet, I just remembered, we haven't yet sort of fully, exhaustively understood how information propagates in a black hole, when a black hole evaporates and so on. For example, you need to show that there's a one-to-one map between initial black holes and final states of the Hauking radiation. I haven't done that yet.
Or the operators also in operators.
The dictionary. But let me also say one thing, that even here, you can show that the density matrix of B is actually not thermal. Right? You can, in principle, compute matrix elements of B, of rho of B. Or said differently, you can compute trace rho to the n for a different n. That probes the matrix element of B, of rho of B. The semi-classical answer, where you don't have any of these wormholes, you conclude that it's a thermal density matrix, exactly. But then if you include these guys, then it modifies it drastically. So this confirms that really this thing is just a prescription. And the density matrix of B really has all that information.
In order to really address the original Hauking situation, you have to say what it is that obeys the page.
What it is that obeys.
What is the quantity that you're computing in this?
This one.
That is fully dynamical.
No.
The density matrix is not.
No, sorry. The situation, the system that I considered, you can phrase Hawking's paradox there.
Right, so this situation has this, but you computed the entropy of the external system.
Yes.
So you could ask if you really just had a black hole, and you would have to define the entropy of the radiation in such a way to obey the Beach curve.
Yeah.
That's I think.
But whether I mean, Hauking would not say you're not allowed to extract this radiation to another system before computing the entropy. I don't think so.
This is a division of the boundary. Like, and if you extract this, so the thing you're computing, as you say, also includes Faraday. So the best way to understand.
No. You're really computing the entropy of radiation. So and here we have a nice way of isolating that radiation from everything else. That's really. No, it is the entropy of the radiation, but the computation for the entropy of the radiation is sensitive to the interior.
But it doesn't commute with operators in the interior.
I agree, but I don't think I'm saying anything contradiction to that.
You might try to define it. Can I say, if you just thought of a black hole and all the radiation.
Yes. Well, it depends. You're computing the entropy of what?
So I'm computing the entropy of the algebra of operators on set.
Or the entire algebra? Then okay, maybe I'd agree with you.
That's what we see. And then there's of course the algebra.
But that's not Hawking's information paradox. Hawking's information paradox is about the entropy of the Hauking modes. That's not the entire algebra.
So what is that?
I mean, I don't know how to precisely define it, but you need to define something like the semi-classical algebra outside. And the claim is that the entropy of that is not going to be zero.
The entropy of that doesn't even have to be that. It doesn't have to ever come back to zero. That also doesn't obey the Beach curve.
Sorry. No, I think it.
Unless you define the entropy of the semi-classical guys, which is that you cut off the algebra, you look at like some endpoint functions with a cutoff.
Okay, no, maybe that's essentially what I'm saying. I think.
Yes, I think that if you really look at the black hole situation where gravity is completely dynamic, there are two regimes. As you said, you can define one way to do the full algebra, one way. One of them just entropy, the other guy just sits at zero. It's not clear what is the guy that goes up and comes down. I mean, maybe there's an intermediate regime, but one way of trying
To isolate that. Yeah.
This is by fiat. There's a boundary. You're seeing a feature of the boundary.
There's a definition of the information paradox.
It's a definition of what you mean by the radiation.
The definition of what you mean by the radiation and the definition of what you mean by the information paradox. It's anyway unique because different people
boundary in two regions of the boundary, and you thought of just some matter being transferred, you would see a page curve.
Maybe that would be interesting to see.
I mean, almost guaranteed to see that. Anyway. I agree, it would be hard to compute. You just took some matter and allowed it to, didn't have to be a black hole.
Yeah, burning coal has a page curve.
Burning coal has a page curve. So this is, I would say.
But that doesn't need wormholes, I guess is the statement.
No, I think this is a holographic derivation of that.
Wormhole that you can see.
Yeah. This doesn't need wormholes, but this is a holographic derivation of the page curve of the boundary. Because, if one looks at the fully gravitational setup, what is
Okay, clearly there's a lot of things to do.
okay.
I just want to give a few examples of, I have a few minutes, of interesting applications of the island prescription. The first is the same space-time, but let's, so that calculation. So let me see. Yeah. So let's compute the entropy just of the right. Okay. Then you find that there's an island, or not. Sorry. There's the quantum extremal surface is somewhere here. It's actually outside of the horizon. So the right boundary does not describe the region near the horizon. You can then try to compute the same thing, but compute the entropy of the bath. Take this at the end. Take the limit of this point reaches this boundary. The limit, not including the point. Then you find that there's no island. Okay, so this bath doesn't describe anything in the bulk. But if you consider the case where you include both of them, so now we have the entire thing. Then you find that the quantum extremal surface is actually here. So I guess I can represent that by drawing a line like this. So the union of the bath and the right bath on the right boundary, it's dual to the entire right exterior. And that makes sense, right? Because you can imagine, so before coupling the bath in, we know that the right is dual to the entire thing. You can imagine this as a unitary transformation, the coupling process, a unitary transformation on R and the bath.
There's no coupling, the coupling was always there.
No, let's consider the case where there's no coupling. And we agree that the right is dual to the entire right exterior. And the entanglement and the quantum extremal surface is the bifurcated horizon. Now let's say we add to the unitary that couples right and the bath. The information about this entire thing is contained in the union of R and the bath. And so therefore it makes sense that the bulk dual of the entire bath and the right contains the entire right region. I'm just saying it comes out of this formula. Okay? So when you compute the entropy of this entire region and you look for the quantum extremal surface, you find that it's a bifurcated horizon. Let's compare these three cases. Here, the right is dual to this region. Just the right boundary.
Which was dual to the full, when you had a coupling or you did not have a coupling?
There's a coupling.
There's a coupling. So the right was dual to...
Just this region. The quantum extremal surface is outside the horizon.
This is some intermediate times.
It equals 0.
And it equals 0.
Yeah, it doesn't. It's time symmetric. It doesn't matter because
all the way to the horizon. It's somewhat outside the horizon.
It's outside the horizon. No, that was my point here. Well, this is a well. I don't quite have a sharp understanding, a sharp explanation why it had to be outside. Actually, no, I think I do have an understanding. Let me not go into that. R is entangled with B and with everything else. I will explain that in a second. Okay? But for now, I want to emphasize that the region near the horizon is not contained in R, nor is it contained in BR, but it's contained in the union of the two. Okay, I want to emphasize that. Okay, now let me explain why it had to be outside. So as a function of time, this thing is, there's a boost symmetry. So the entropy of R, the quantum extremal surface, is there at a later time. Remember I had a discussion about the Hayden-Preskel protocol. So if I send information into R, I should lose it after some time. And the fact that it's not on the bifurcated horizon achieves that for me. Because I can send a message here. At t equals 0, the message is inside the entanglement wedge of R. So it's part of R. But at this time here, it's not inside the entanglement wedge of R. It escaped. So at this time, the right has forgotten about this message. Okay? And in fact, you can show that the minimum time you need to wait for the message to escape the system is precisely the scrambling time. So now we're reproducing the results from Hayden-Preskel. This is beta over 2 pi log the entropy, the thermal entropy of the black hole. So Bekenstein-Hauking entropy at temperature T minus the ground state entropy. So the scrambling time is governed by the entropy above extremality. This actually has been observed in studying out-of-time ordered shock waves in a near-extremal black hole by Stefan Leichenauer and Lenny and friends. But the point here is that we've recovered the prediction from Hayden-Preskel, okay, that the information escapes after a scrambling time. Okay. Another case to consider is the t equals 0 case. I think this is really interesting. The t equals 0 case is the following. So I have just a Poincare patch. And I've eternally coupled it to a bath, also at 0 temperature. You find that the entropy of R, or the quantum extremal surface of R, ends there. Because the state of R union the bath is pure, if you compute the entropy of the bath, then you find that there's an island here. So this is for the near extremal black hole. And this is very interesting. It tells you that if you buy that this is a toy model for near extremal black holes or extremal black holes in higher dimensions, then after some point down the throat, this region here is actually dual to the asymptotically flat region far away. In some sense, this physics deep down in the IR and deep in the bulk is captured by IR physics far away. And I think that's an interesting point. This is a one-sided situation, yes. This is just an extremal black hole. Why is it surprising?
Yeah, I mean, it's just what we discussed earlier, right? You take the asymptotically far region and describe everything. Now you're taking the algebra, everything about it. It is really the algebra. So.
Okay, you can think of it as a realization of what we said. Yeah, I think I think there should be a bunch of graduate students that are applying this formula for all possible spacetimes and finding surprising results. Okay. Okay, yeah, that's all I had again.